Welcome back. We are now into lesson 4, which is a new operation in R3 called the cross product. So we're going to define the cross product in R3. You can take the cross product on multiple vectors, which is why I had written cross products. I wanted to do a quick overview of all the operations we've talked about so far and contextualize this new one before we actually introduce it. Let's recall all operations we've seen in R3 up to this point. The first operation that we saw in R3 was called the to-norm. And this operation had special notation. I put the little dot to represent that there should be something inside. Otherwise, it kind of looks strange. You could write it like that. Just the dot says, okay, something goes inside of that thing. The to-norm went from R3 into R. And what this meant was that the domain of this space was R3, which means that we have a single input, which is a vector with 3 components. So that's what it means when we write there. And we said that it mapped into this space R. We call this the codomain. It's not the range, right? This means that the output is a real number. The range would be the set of actually achieved outputs, not possible outputs. In that case, we would write the 0 to infinity, including 0, because the to-norm is always positive, non-negative anyways. Okay, that was the first operation that we saw in R3. The second operation that we saw was known as vector addition. And this operation went from R3 with 2 copies into R3. So this is the domain of this operation. And what it says is we input to the vector addition symbol 2 vectors, each with 3 components. So on the left, we put a vector of R3. On the right, we put a vector of R3. And then the output of this is a vector in R3. I think it's actually worth noting now, rather than in a little bit, the physical significance of each of these. The to-norm was used to measure the length, or some people call that the magnitude of vectors. And it also can be used to measure distance between vectors. We haven't talked a lot about this in the videos, but we did do some problems like this. If I take the to-norm of vector u minus v, that's the measurement of the distance between the 2 of those vectors. All right. Vector addition was really useful to produce new vectors from a set of old ones. and you might call, or old vectors. You might this useful combine vectors together. And the quick geometric observation is, let's say you had two vectors, one in this direction and one in this direction. You could get to some vector out here by adding those two together, right? You've got these two different directions, and then you get this third option through addition. And that's what we use vector-vector addition for. All right. We then had a third operation, which we called scalar vector multiplication. And this one used the same dot that we know and love. God, we just love to abuse notation in mathematics, huh? A bunch of lazy bums. Of course, we want to say, no, we're quite efficient. But we know the truth, huh? Yeah, okay, so the idea of scalar vector multiplication was that the domain, the thing that we wanted to analyze of what we're putting in, requires a scalar on the left-hand side and a vector in R3 on the right-hand side. And then the space that we map to the set of outputs is our vectors in R3. We said that the scalar vector multiplication operation was super useful to stretch vectors. Stretch. I think I spelled that stretch. Oh God. To lengthen or compress vectors and to change orientation. And we could do a quick observation here. If you have a vector, let's say that you have a vector x going off in this direction, you could lengthen this vector, you could make it longer, you could stretch it out by multiplying, let's say, 2x. And of course, this should be a vector. You could compress x by multiplying, I don't know, by a fifth perhaps. Maybe you call this 0.2 times x, so you can compress it. And then another thing is you can change the orientation. Right now, x is oriented here, which means it goes from the initial to the terminal out in that direction. You could look at going in the opposite direction by taking the negative. You don't want to use the word I don't want to use the word opposite direction, because direction again is any scalar multiple, right? What I mean is we're now reorienting around that point. So it's like a rotation around that point. That's a major form of scalar vector multiplication. And then the other thing that I want to say is scalar vector multiplication is also super useful when defining lines and directions in R3. Remember that the direction of a vector x is the set of all scalar multiples times x. This is going to come back over and over and over again. I wanted to say come back to haunt us, but I hope that if we have this in our memory, it will instead please us. It will make us smile every time we see it, as if it's raining money down onto our bank accounts. Oh, no. Okay. So those are the first three operations. In lesson 3, we talked about a fourth operation, which was called the dot product or inner product. I'm going to be a little bit more stuffy or proper, and I'll call it the inner product. If I wanted to be cool and young, I might call it the dot product. All right, the inner product operation, we said, was used the same dot symbol as we saw before, and it went from R3 cross R3. This is a set cross, not a cross product like we're going to talk about today. I don't know that I want to get into that because it's not a requirement for this class. Remember, it's just a placeholder. It says whatever's on the left of this is the size of the left argument. Whatever's on the right is the size of the right argument. So the domain of the dot product says that the input is 2 vectors in R3, and the set of possible output, the codomain, is a real number. And this is really special, right? You take in 2 vectors and you produce a real number. And we're going to come back to this because this is one of the major differences between the cross product and the dot product. The cross product will not produce a real number. Remember that the inner product or the dot product was super useful as a measurement of parallelity between vectors. And the tagline, if we were to write a commercial with a little jingle, we would say that this is the tagline. This would be the jingle. And I'm not going to sing to you because I don't want your lawyers to contact me for ear damage. Okay. So that's the tagline, right? We said that the parallelity was combined in the cosine. The other thing that the dot product was really used to do was to project one vector onto another, useful to orthogonally project one vector onto another. And I have to say this, the current technological world is brought to you by orthogonal projections. There's a reason why I spent so much time on that in the last video. You might be like, oh my God, he's just droning on. Why does he show all this? And I'd be like, yeah, you're right. If your goal is just to solve problems that come from a calculus book. If your goal, however, is to initiate yourself into the 20th century, 1900s, 1950 to 2000s really, use of technology, use of mathematics to drive technology, the orthogonal projection is a fundamental tool used in so many different fields. In fact, Fourier analysis is based on this concept. Many of the numerical algorithms that run on your computer, wavelet bases that are used in iTunes. I mean, I could go on and on and on. I don't know. I'm going to say it. Today, I'm going to say that if I had to choose one tattoo to get on my arm, it would be of orthogonal projections. If you ask me tomorrow, I might have to get a different tattoo. But these are super powerful in modern technology. And that's why I wanted you to spend so much time in lesson 3, really getting your head around it in your first introduction. Okay, so the idea of this was to project this vector down, and then we can orthogonally decompose one vector as the amount of this vector in this direction, and then the amount of the vector directly orthogonal to that direction. Okay, so those are now the 4 operations that we've done so far in R3. This video is an introduction to the 5th operation. And this is going to be what we call a cross product. And the cross product is interesting because for once, thank God, we're not using that stupid dot symbol. And that beautiful, wonderful, amazing dot symbol. We're going to use the time symbol instead. And I want to be careful. This time symbol is different from this one. Remember, this was a placeholder. really it's a cross product between sets. Don't worry about that. This thing is a cross product between vectors, which means on the left-hand side of the cross product between vectors, we have a vector. On the right-hand side, we have a vector. So here's the domain of the cross product. And this means that the input is two vectors. So notice it's a product between vectors in R3. And then the output, look at the size of the output here. This is one of the first ways that you can start recognizing that this is a little bit different. The output is a vector, not a scalar. Which is pretty amazing. There's a note to be had here. This is the only operation that exists uniquely in R3. This is unique to R3. If you were to ask me as a mathematician, is it really unique to R3? I would come back, well, there's one in R7, but it's not, doesn't hold with the same algebraic properties. And outside of R3 and R7, there actually are no cross products based on what we want it to do. And you can find a kind of a nice description of this on Wikipedia. I'm not going to get into that because that's out of the purview of this class. But what I want to say is all of the other four operations that we did exist in any space, R2, R3, R4, R5. The cross product is the unique operation that we will study in this class, in the first part anyways, that exists only in R3. It's kind of cool, right? Let's continue with our pattern of analyzing why these are useful. This one is useful to take two vectors and produce a third vector, the output, that is orthogonal to the two input. To the original vectors, that's the word vectors. And some of you had said, hey, Jeff, write so that we can see what you're writing. And I love that suggestion. The right-hand rule is actually a really good way to think about this. So when you think about it intuitively, think right-hand rule. Okay, I take my right hand, I point in one direction, I point in the other direction, and then the whole idea of the cross product is the cross product will allow me to get the direction that's orthogonal to both of those, right? So the right-hand rule is your first example. When you were doing the right-hand rule, you were actually getting the cross product between these two directions, which is pretty amazing. You got to be careful with the right-hand rule because you never know where your middle finger is going to point. In other cultures, you might not have to, but in America, those are fun conversations, right? Okay, so when you're looking at the cross product, the first thing that we're going to do is it's useful to take a vector that's orthogonal to another two vectors. And then the other thing that is kind of interesting about the cross product is we'll see that this is a useful tool as a measurement of perpendicularity, right? You can think about this as how much two vectors are perpendicular, or you could call it orthogonal. This is intuitive, so I'm trying to get away from formal language. Okay, so there are a few different things to notice. The cross product takes in two vectors, each of size 3, produces a vector of size 3. We're going to do two things with the cross product. The practical thing that we'll use when we're solving problems is we're going to produce a third vector that is orthogonal to the first two. And the way that we do this is we actually think about this as a measurement of perpendicularity. And that's how we're actually going to construct the component definition, which we'll see in the next video. All right, hopefully this gives a useful overview of what we've done so far and also starts contextualizing about what lesson 4 is all about. In the next video, we'll actually derive and construct the component definition of the cross product using this intuition. I'll see you in the next video.